First of all, I would like to thank Professor Kwak and Professor Schreier for having me in this conference or in this workshop. And I would like to also thank everyone for coming. So today I would like to talk about what I did this summer. So I thought, giving such a talk may be a little bit premature, but I also thought, I might be able to get some feedback from the audience. So I decided to give this talk. So what is the discriminant? So the discriminant of a polynomial is an irreducible polynomial which vanishes at a homogeneous polynomial whenever the polynomial has a multiple root. And so you can take a look at discriminant of a polynomial from a slightly different angle. So namely, a homogeneous polynomial can be viewed as a global section of a line bundle. So what I would like to do today is to extend the concept of the discriminant of a line bundle to a vector bundle of a higher rank. And I believe there is some general theory because the problem itself is very natural to think about. And I would guess that there is some general theory to answer some of the problems I'm interested in, but so I would like to talk about what I did. Okay, I'm sorry, but this. So first of all, what I would like to do is to explain. So what happens if you have a vector bundle and if you choose a global section? How can you describe the global section in such a way that you can actually use it in a computer? Okay. So in the first slide, I listed some of the letters and symbols I'm going to use throughout this talk. I hope most of them are commonly used. So I'm not going to explain what these are. So let's just consider a vector bundle of rank R. On Pn minus 1, so I'm going to assume the rank is less than or equal to n minus 1, because if rank is equal to or bigger than or equal to n, then the section can be viewed as an overdetermined. So it defines just the empty set. So I would like to just restrict my attention to the case where R is less than or equal to n minus 1. Okay. So let's pick a global section of this vector bundle. So this vector global section also can be viewed as a sheaf morphism from O to E. So now I'm going to flip this sheaf morphism to get S dual. So this is sheaf morphism from the dual of E to O, the structure sheaf. Then the image of this sheaf morphism is a subsheaf of the structure sheaf, which is just an ideal sheaf. And the corresponding closed subscheme in a piece of n minus 1 is called the zero scheme of the global section. So locally, a global section can be viewed as a collection of R coordinate functions. So what does it mean? So this means the codimension of the zero scheme of the global section is less than or equal to R. Now if the codimension of the zero scheme of the global section is equal to R, then we call the section regular. So now I hand you a vector bundle on the global section. And I would like to ask you to tell me some information about the zero scheme of the global section. For example, you can ask whether or not the zero scheme of a global section is irreducible. If not, it is not irreducible. So you can also count the number of irreducible components, or you can also ask the dimension of each component or degree of each component. or you can also ask whether or not each component is singular or non-singular. Okay, so since I would like to talk about the discriminant, so I would like to tell you how you can check whether or not the zero scheme is singular. So this is how I would do. So since E is a coherent sheaf, and that means the dual of E is also a coherent sheaf, and the zeroth cohomology module is finitely generated. So that means you have a surjective R module homomorphism from the direct sum of rank 1 modules to the cohomology module of E dual. Okay, so now you're going to sheafify this, and then you get a surjective sheaf morphism from the direct sum of line bundles to the dual of E. Okay, so now I'm going to flip this. That means we take the dual, and you get an injective sheaf homomorphism from E to the direct sum of line bundles. Okay. So remember, if you have a global section, this global section can be viewed as a morphism from O to E. So now I'm going to composite this phi and S. So this is if you the composite of phi and S is a morphism from O to the direct sum of line bundles. Okay, so if you use the canonical basis for both source and the target, you can represent this sheaf morphism as a column vector with whose entries are homogeneous polynomials. So these homogeneous polynomials cut out the zero scheme theoretically. So I'm going to use these homogeneous polynomials to study the zero scheme. So as I said, I'm interested in whether or not the zero scheme is a singular. So first of all, I would like to assume S is regular. So remember, S is regular means the codimension of the zero scheme is equal to R, which is the rank of the vector bundle. Okay, so I'm going to form an ideal by using the homogeneous polynomials F0 up to Fl minus 1, and I take the Jacobian matrix of the generators for this ideal, and then you can form an ideal by taking an R by R minus of this Jacobian matrix. And a projective version of Jacobian criterion says Z of S is singular at P if and only if P belongs to the variety defined by I plus J. Okay. So now I would like to take a look at a couple of examples. So here we have a 3 by 3 matrix. So that represents the sheaf morphism from this direct sum of line bundles to this direct sum of line bundles. And I'm going to consider the image of this sheaf morphism. Okay. So this sheaf corresponds to the module generated by the columns of this matrix. Okay, and I'm going to say this is a rank 2 vector bundle on P sub 2, or P2. So this is because, first of all, so if you take the determinant of this matrix, you get 0. That means, so these 3 columns are always linearly dependent. But if you take the 2 by 2 minors, so the corresponding ideal, or the radical of the corresponding ideal is the irrelevant ideal. So that means, so these 2 columns are linearly independent. at every point on the projective space. Okay, so therefore this E is a rank 2 vector bundle. So this vector bundle also can be viewed as the cokernel bundle of this morphism. Okay, so you can take a look. Sorry?
Change the twist.
Probably what I should have done was, I'm sorry, thank you. I'm sorry, that's the correct twist. Okay. So this is a syzygy among the generators of this module, and this is so every syzygy can be written as a scalar multiplication of this syzygy. So you have this exact sequence, and it can be viewed as the cokernel of this sheaf morphism. Okay. So one thing you can tell is H0 of E is isomorphic to H0 of this vector bundle. Okay, so that means, so if you pick a global section of this vector bundle, and you have a unique section of this direct sum of line bundles. Okay. So I'm not very organized. So now how can I find how can I represent a global section? All we have to do is just multiply phi and A. So in this case, we get 3 linear forms. And one thing you can say is if S is not 0, then the zero scheme consists of a single point. So what does it mean? So that means the zero scheme of every non-zero section is non-singular because it consists of a single point. Okay, so now I would like to twist this vector bundle by O1 and see what's going to happen. So one thing we have to take into account is, so let's suppose phi 0 and phi 1 and phi 2 are columns of phi. So then we have a syzygy among these generators. So namely x0 times phi 0 plus x1 times phi 1 plus x2 times phi 2. That must be equal to 0. Okay, so that tells us for each global section of E of 1, so there exists A, in this case instead of A0 constants A0, A1, A2, so we have linear forms, 3 linear forms. we have three linear forms such that S is equal to phi times A. Okay, so if you pick some numbers for A0, A1 up to A9, A7, so you get a section, explicit section. So let's pick for example, so I'm going to pick this 0 and negative x1 and negative 3x2. Then phi s, which is phi times a, is equal to x0, x1, and negative 3x0, x2, and a 2x1 and x2. Okay? So now I'm going to use these homogeneous polynomials to define the ideal for the zero scheme. So the zero scheme of S is defined by x0, x1, x0, x2, and x1, x2. Okay? And if you, for example, use Macaulay 2 and compute the primary decomposition, you get x0, comma x1, x0, comma x2, and x1, comma x2. So each primary ideal corresponds to a single point. So the zero scheme consists of three distinct points. So that means the zero scheme is not non-singular. So is this example clear? Okay, so now I'm going to take a slightly different vector. So it consists of x1, 0, and x2. And then we get x1 and x1 squared, x1, x2 minus x0, x2, and negative x1, x2. Okay, so now I'm going to form an ideal for the zero scheme, so which consists of so x1 squared and x0 and x2 and x1 and x2. So now I'm going to use these generators to compute the Jacobian matrix, and the Jacobian matrix is, if I did it correctly, this 3x3 matrix. And if you evaluate this Jacobian matrix at a specific point, so for example, P is equal to 1, 0, and 0, and you can easily see so the Jacobian matrix evaluated P is this 3x3 matrix, and of course if you compute the 2x2 minors of this matrix, you get 0. Okay, so that means G of S is singular at this point. Okay, I hope I believe many of you already knew how you can represent a global section of a vector bundle if you have a vector bundle explicitly. But anyway. So now I think we are in a position to define the discriminant of a global section of a vector bundle, which I actually defined at the beginning of the talk. So let's assume E is a vector bundle of rank R. Again, I'm assuming R is less than or equal to n minus 1. And H0 of E does not vanish. Okay, so that you have a non-zero global section. Then we can define a delta of E as the Syzygies closure of the set of equivalence classes of global sections whose zero scheme is singular. And if this delta E is not empty, so it could be empty, then we call it the discriminant variety of a global section of E. For example, so we discussed a couple of examples in the not previous slide, but on the board. And so we discussed E, which is defined by a 3x3 matrix of particular type. And then so every non-zero we saw every non-zero global section defines a single point. So zero scheme of every non-zero global section is non-singular. So that means delta E is empty set in this case. However, in the second example, so I twisted E by 1, and there is a global section whose zero scheme is non-singular, but we also showed the existence of a global section whose zero scheme is singular. So for that E, delta E is non-empty. Okay. So that's one example. The example is the case where E is a line bundle. Okay, so E can be written as O of D, where D is some non-negative integer or the positive integer. Then delta E is the set of singular hypersurfaces of degree D in Pn minus 1. Okay? So this delta E is also interpreted as the dual variety of the D Veronese embedding of Pn minus 1. So by using this interpretation, you can prove that the discriminant variety is actually irreducible hypersurface, and you can also compute the degree of the hypersurface. Okay, so now we defined the discriminant variety. So you can ask a couple of basic questions about the discriminant. So the first question would be, so how big is the discriminant variety? How about the degree? Can you prove irreducibility of the discriminant variety? So this talk is basically related to all these questions. Okay, from now on, so E denotes always a vector bundle of rank R on Pn minus 1, but additionally, I'm going to assume the following three conditions. So E satisfies the following three conditions. The first of all, H0 of E is not equal to 0. And a generic global section is regular. And the last one is the dimension of the projective space of global sections is bigger than or equal to n. So this condition is looks a little bit weird, but that guarantees the discriminant or delta of E is not empty. Okay, so what I'd like to do is to estimate the dimension of the discriminant variety. So my approach is very naive and very elementary, and I'm going to use the instance correspondence-like variety. So I of E denotes the set of Zariski closure of the set of pairs of points in Pn-1 and equivalence classes of global sections of E such that the zero scheme of S is singular at P. Okay. So this set sits inside Pn-1 cross P, the projective space of the global sections of E. Okay, so you can consider two projections, one to the first factor and the second one to the, the second one is to the second factor. Okay, so I'm going to write pi I for the projection of Pn-1 cross Ph0E restricted to I of E to the ith factor. Okay, now all I'm going to do is just consider the fiber of pi 1 and pi 2 at generic points. So I of E could be reducible, but I don't need to consider all possible components. I'm going to pick one of the largest components and measure the dimension of I of E. So I sub 0 of E is any irreducible component of I of E such that pi 1, the image of I0 under pi 1 is equal to Pn-1. And then we can consider the upper semi-continuous function, which is defined by sending P to the dimension of the fiber of pi 1 over this P. Okay. So nu denotes the smallest such integer, and lambda sub 0 of E denotes the image of I sub 0 of E under pi 2. Then we can also consider another upper semi-continuous function, which is defined by sending the equivalence class of a global section to the dimension of the fiber of pi 2 over that equivalence class. So rho is just smallest such positive integer or non-negative integer. Okay, so that measures. So since I took bracket S from the discriminant variety, so the corresponding scheme is singular. So rho measures how big the set of singularities is. Okay. Then the dimension of I sub 0 of E is equal to n-1 plus nu. And the dimension of delta 0 of E is equal to the dimension of I0 of E minus rho, which is n-1 plus nu minus rho. And the rho is the rho could be 0. That means the zero scheme has only isolated singularities, but the zero scheme itself could be also non-reduced. So then rho is equal to n-1 minus r, which is the dimension of Z of S itself. And the question is, what can we say about nu? Since the concept or notion of a singular scheme is local, so I think we may restrict our vector bundle and its global sections to an affine open affine subscheme. So what do I mean by this? So in 1976, Kubilin and Syzygies independently proved the so-called cells conjecture, which states every finitely generated projective module over a polynomial ring is free. So what does it mean to us? So that means if you have a vector bundle of rank R, and if you restrict your vector bundle to the complement of a hyperplane, so in this case I'm just using the coordinate hyperplane, then that guy is isomorphic to just the direct sum of line bundles. Okay. So that means if you restrict your global section to that complement of the hyperplane, this can be written as a collection of all polynomials. So the zero scheme of a global section may be defined by a larger number of polynomials, but we are taking the advantage of the fact that this is coming from the global section of a vector bundle, so that we can always have exactly R polynomials to use. And for simplicity's sake, so let's assume that P sits inside the complement of the hyperplane defined by x0. So whose coordinate ring is just the C adjoint x1 up to xn minus 1. Okay. Then Z of S is singular at P if and only if the following conditions are satisfied. So this is just a fine version of the Jacobian criterion. So first of all, F1, so if you evaluate F1 up to Fr at P, you get 0. Okay, so that's the first condition. And a Jacobian matrix of these polynomials has rank strictly less than R. So the nice thing about Fi's and the entries of the Jacobian matrix are, so if you evaluate these polynomials at P, so these are linear forms in A0 up to AL minus 1, where A0 up to AL minus 1 are homogeneous coordinates of the projective space of the projective space of global sections. Okay, so now I can form an ideal by using R linear forms, F1P all the way up to Fr of P. And we can also consider the ideal generated by the maximal minors of J of S evaluated at P. And the codimension B of I is less than or equal to R because we have all linear forms. Okay. And the codimension of V sub J is less than or equal to the dimension of the determinant variety of R by n minus 1. I mean, generic matrix, generic R by n minus 1 matrix. So whose codimension is n minus R. So the codimension of V of J is bounded from above by n minus R. So that means the codimension of V of I plus J is less than or equal to R plus n minus R, which is n. So what we proved is nu. Nu is just the smallest integer or smallest value of the upper semi-continuous function defined by sending P to the dimension of the fiber of pi 1 over P. So nu is bigger than or equal to R minus L minus 1 minus n. And since we assumed the dimension of the project space of global sections is bigger than or equal to n, so nu must be bigger than or equal to 0. That tells us if you fix an arbitrary point of P, then the corresponding fiber is non-empty. Okay, so that means every time if you pick a point on projective space, you should be able to find a global section whose zero scheme is singular at that point you chose. So the dimension of I sub 0 of E is equal to n minus 1 plus nu, which is bigger than or equal to n minus 1 plus L minus 1 minus n. And if you simplify this expression, you get L minus 2. Okay, so that means the dimension of delta 0 of E is less than or equal to L minus 2. So to be honest with you, I think there is a correlation between rho and nu, which I should have taken into account. And I believe, this nu and rho are balanced out in the end. So I think the dimension of the delta should be equal to L minus 2, which is a hypersurface of a projective space of global sections. But I'm sorry, I forgot to take it into account when I'm making these slides. Oops. Okay, so we have lower bound and upper bound. So lower bound is obtained by assuming the zero scheme itself is non-reduced. So, but I believe that delta 0, the dimension of delta 0 should be L minus 2 instead of, there is a range for the dimension. I'm sorry, you saw already a thank you slide, but there is one example I would like to discuss before saying thank you. Okay, so now I think we have a very good idea of the dimension of the discriminant variety. So it seems to be a hypersurface. But the question is, how can you actually find the degree of the discriminant hypersurface? So this is what I actually wanted to talk about next time. But I would like to also get a peek at what I'm going to talk about next time. Okay. So, example. So I would like to consider a line bundle on P1. And the question is, so what is the degree of delta of E? So this is the classical discriminant of a polynomial in one variable. So we know actually the degree, but let's pretend we don't know the degree. Okay, so if you know the resultant, you can compute the resultant of f and f prime. So f and f is a polynomial of degree d. And then you can compute the resultant, and you have to divide it by the leading coefficient. So that gives you 2d minus 2. So we know actually the degree, but let's pretend we don't know the degree. And we don't know the concept of the resultant. And the question is, how can we find the degree of the discriminant of this vector bundle? So by the way, if you have a hypersurface, how would you compute the degree of the hypersurface without finding the equation? Yeah, that's right. So one thing I would do is just pick a generic line and poke the hypersurface and count the number of times, so how many times this line meets the hypersurface, right? So that's what I'm going to do. So I pick two global sections of this vector bundle E. Then I'm going to consider the line spanned by these two global sections. So this can be considered as a generic line. Now I would like to see how many times this L meets the hypersurface. Okay. So now I'm going to consider C, which is the disjoint union of the zero schemes of lambda S1 plus mu S2. Okay, so if you fix lambda mu, so you get the zero scheme of a single global section, right? And this global section has exactly two zeros counted with multiplicity. Okay, so if you move lambda mu, and then you get also a curve. So this C is a curve. But this is there is another interpretation of this curve. So this curve is also obtained as so-called the dependency locus. That means this is the set of points where S1 and S2 are linearly dependent. Okay. So our vector bundle is a line bundle. So I pick two global sections. So what is the dependency locus of these two global sections? So E is a line bundle, right? So that means they are always linearly dependent. So the dependency locus is just P1, so the entire space. Okay. So now I'm going to define a map from C to P1. Okay. So this pi sends so let's suppose P is a point on the curve, and a pi of P is equal to lambda colon mu if and only if P sits inside the zero scheme of this global section. Okay. So here's the key remark or key observation. So the global section or equivalence class of the global section lambda S1 plus mu S2 sits inside delta E. This happened if and only if C is ramified at some P in the zero scheme of this global section. So what does it tell us? So this tells us the degree of delta E is equal to the degree of S, where S is ramification divisor. Okay, but how can you compute the degree of the ramification divisor? So we have Hurwitz Riemann formula, right? Which says 2 times the genus of C minus 2 minus the degree of pi times 2 times the genus of P1 minus 2. Right, so this is what Hurwitz's formula tells us when we want to count or compute the degree of the ramification divisor. So we know C is P1, so that means this is 0. Wait a minute. Something, yeah, this is, I'm sorry, this is T 2z of C minus 2 instead of 2 times zc minus 2. So z of C is equal to 0, so that means you have negative 2. And what is the degree of pi? Yeah, D. And the genus of P1 is 0, so you have 2D minus D. 2D minus 2. Okay, so I think I said everything I wanted to say, but let me just say what I'm going to do next time. So next time I would like to focus on the discriminant variety of a specific rank n-1 vector bundle, which is called a Schwarzenberger vector bundle, which is a rank n-1 bundle on Pn-1 in a very particular form. And I would like to prove that the discriminant variety is a hypersurface and irreducible, and I would like to compute the degree of the hypersurface. And if time permits, I would like to explain to you why I got interested in the discriminant of a global section of a vector bundle. Okay. So thank you very much.